This is an introduction to experiment 1J. As you'll see in the lab manual, there's essentially A through J, experiments that I've used in various years. This is 1J. Skip all the other ones. I know that I left them in there, but just skip through them. So do 1J. So this part is essentially what you're going to do is read a value from a ROM and look at that value, and you're going to sort it based on what that value is. And so that value is either going to be ignored or placed in one of two RAMs. And those two RAMs, which RAM it goes in and whether it's ignored or not, are just based on the magnitude of the value that's read. So that's really super high level. But a couple issues here. I want you to display certain stuff in certain order. So when you're actually sorting the numbers, I want to see the number on the display on the development board. After it's sorted, what it's going to do is step through each RAM, every address in each RAM in order, and then go to the next RAM, then go back to the other RAM. And essentially what it's going to do is display an address and display the value. So the key here is it's using two different display modes for these two different functions. And so the 7-segment display module supports the two different display modes, and that's a module that's provided for you. You don't have to worry about designing that. Constraints for this thing is I want you to use only standard digital models. I don't want you to use magic circuits in this thing. I don't want you to use mathematical operators anywhere except in the ripple carry adders, which you don't need for this, or the counters. You will need a few counters for this design. This design is going to be controlled by a finite state machine, and I want that no more than 6 states in this thing. It could be done very easily in 4 states, depending on how you do it. And the state machine needs to be completely independent of the RAM and ROM size. State variables are the only memory in the state machine. Don't try to put any extra memory in the state machine. Don't put input data to the state machine either. That should be done external to the state machine, which once again makes it generic and 100% independent of the RAM size. So the experiment has a bunch of other details. Go check the lab manual for the other details. Lots of resources on Canvas. When I say use all the standard modules, let's use them, plop them down there. It's kind of like a cut and paste. Just plop them down there. They are mostly generic templates, so instantiate them, and then override the default values. Do not change the module themselves. And the issue here is for any time you drop a module down here, what you want to do is make sure all the inputs are assigned, and then you leave the outputs blank. Do not remove any line from the template. And notice that all these modules except the state machine has a instantiation template which allows you to cut and paste, and it's actually very, very quick, and so you don't have to change any of that stuff. But once again, make sure every input's assigned, and make sure all the outputs, if you're not using them, are just blank. Lots of standard modules out there. There's also some generic RAM out there. If there's not, there's actually only one ROM out there and one .mem file. Sorry about that one. That was from the last experiment. There is a FSM template module out there which I always use as a starting point. It does not have a template in it, so be careful with that. It doesn't have an instantiation template. But most importantly here, we do have a 7-segment display module, so you don't have to write that one. But you're going to have to run it in different modes. I wrote the 7-segment module a while back, and I don't know how it works, but I put all the information I need to know in the header of that particular model. So go check that out. It gives you all the information you need. You don't need to understand exactly how the module works. Quite honestly, it was the first Verilog module I wrote, and it's kind of an embarrassment, so try not to look at it. Anytime you have a design problem, you're going to have to develop your own design style. And this is mine. First I understand the problem, and then I select the modules and plop them down on a piece of paper. I connect them up, and that connection means, you know, all the control and data lines and status lines too. And then I start with a state diagram. I take a state diagram and make sure that state diagram can control that circuit. And really, if it can't control it, I just go fix it. It's not a big deal. I don't think I've ever in my life got it right the first time. I always go back and fix it. Remember, design is circular. It's not linear. You're expected to go back and fix stuff. I'm not smart enough to get this right the first time. So anyway, this is just a reiteration of the last slide. Keep it super simple. It is, like I said, an iterative design process. You're going to make mistakes. You're going to have to go back and fix them. Typically, you try to wing it, which I try to do, but I always end up going to the simulator to fix my problems here. Along the way, ask questions, send me circuit diagrams, send me state diagrams, send me anything you can to help. Just don't send me emails saying, hey, it doesn't work. I'll need more information than that if I'm going to help you. This is the top level of the circuit. No big deal there. It does have a button to make it go, and then the rest is just associated with the 7-segment display device. So it's due, this is a funny quarter, so it's due Monday, about 2 weeks plus a couple days, which is essentially, I think, the seventh class meeting of the quarter. And that's it, folks.